All right, let's talk about the refraction of light waves. So this is going to be the refraction of light. So what this is representing here is beams of light on their way into a plastic brick, and they're passing into this secondary material, refracting once, and then passing back out into air. Okay? So I'm just going to label some things here. Here's air, right? Here's acrylic, which is, clear plastic, a type of clear plastic. And here's air. Okay? This is a source of light. We'll just call it S. And there's some reflection going on. So we have waves traveling out of the source, striking the surface. I'm going to put a normal line there. So let's draw in a normal. Okay, so there's a normal. I can't seem to grab this. There we go. There's a normal. And you'll see there's some reflection. I'm not all that interested in reflection, but it's interesting to kind of notice that there is, reflection going on here. But what we're interested in is we're interested in the refractive, the two refractions actually that are going on. So there's that one. And then there's also the next refraction, which happens over here. There's also a refraction going on right here as well. And let's just change the color. Double refraction, yes. I know what you're doing. Complete double refraction. Okay. So let's just talk about what's going on here. Now, what does it mean if when light is entering the acrylic block, it bends towards the normal? What does that tell you about the velocities that we're dealing with? Now, just remember, we had this relationship from a past video here. And we are getting a theta 2 with a smaller value. So what that must mean is light traveling slower or faster inside the acrylic block? So looking at these pictures here, what you should be able to realize is if, where's a nice color here? How about this one? Here's theta 1, right? The angle between the incident wave ray and the normal. And here is theta 2, okay? Theta 2 is a lower value than theta 1, hence velocity 2 has to be a lower value than v1. So just by looking at this picture and understanding this relationship, okay, we can say light travels slower in acrylic. Okay? Now I'm just going to introduce the index of refraction, and then we're going to be nearly out of time. So index of refraction. This applies to optical media. Okay? In other words, stuff that light can travel through. And the key to understanding this is that light travels more slowly. Is slower a word? I think it's more slowly. I'm going to put dense here, in dense optical mediums, or media, in dense optical media than it does in vacuum. Okay? And optical medium are defined an index of refraction based on the following fraction. N equals V over C. And let's just fix this. Sorry, I just realized I wrote this upside down. It should be C over V. C over V. Now, what is c? C is the speed of light in a vacuum, and v is the velocity of light in medium. Okay? So that's called, and this n here is called the index of refraction. Do you remember in Snell's law that we wrote out, you saw n1 sine theta 1 equals n2 sine theta 2? This n is representing the index of refraction for medium. Okay, so let's do a quick example, and then we'll have to wrap it up. So find the index of refraction for a plastic in which light travels at 2.5 times 10 to the 8 meters per second. Now, c, the speed of light in a vacuum, is 3.0 times 10 to the 8 meters per second. So what we would get is that n in this plastic, or the n value for this plastic, the index of refraction, is 3.0 times 10 to the 8 meters per second. So c over v, the velocity in that medium. And the value you would get is 1.2. There are no units. Meters per second would cancel out, so it's just that ratio. Okay, the coefficient essentially is what it is. The coefficient of refraction. So it's 1.2. And that is it for today.